Good day, and welcome to the USDA Climate, Agriculture, and Forestry Science Seminar Series conference call. Today's call is being recorded. At this time, I'd like to turn the conference over to Louis. Please go ahead.
Good day, everyone. Welcome to this webinar. I am Louis Tupas, the Deputy Chief for Soil Science and Resource Assessment at the Natural Resource Conservation Service. This webinar series is intended to build a better understanding of the scientific foundation of climate change's relationship to our working lands to ensure a climate-informed workforce for USDA, the US government, and important stakeholders. Our inaugural webinar is an introduction to the physical science of climate change with particular focus on issues of interest for working lands. Before we begin, I would like to invite Mr. Bill Hohenstein, the Director of the USDA Office of Energy and Environmental Policy, to provide some welcome remarks.
Thank you, Louis, and welcome everyone. I'm Bill Hohenstein. I'm the Director of the Office of Energy and Environmental Policy here in the Office of the Chief Economist. And we have, one of our responsibilities is to coordinate our efforts on climate change. And we've been busy. It's been quite a year. The role of USDA in addressing climate change is critical to overall national success. As I tell farmers and ranchers and forest landowners that we're on the receiving end of climate change. Much of what we'll need to do to prepare for climate change will be to build resilience and adaptive capacity within the resources we manage and among the people that we work with across the country. We have two documents that we've prepared over the last year that should help us in that. A mitigation plan, something called a progress report, the 90-day progress report, and a formal adaptation and resilience plans for the department. In addition, the agencies across the department come together and meet as part of our Global Change Task Force. And so each agency with some responsibility for climate change is represented in that group. One of the tasks we have at hand is to ensure that we have a climate-informed workforce, that the staff of USDA understands climate change and the implications. As we ask you to consider climate change in your work, whether that be the work of NRCS or Forest Service or risk management, it's important for us as a program to give you the information you need to be successful. In the past, when we've asked our staff to address climate change, the question generally I get back is, tell us how the climate is going to change and we can begin to manage for it. And so really that's at the heart of what this seminar series is about. So as Louis said, this is the first in a year-long series. We're going to be doing this once a month, covering the wide range of issues that relate to agriculture, forestry, natural resources, and climate change. This first session deals with the core science. What do we understand? What do we know? And why are we confident that the climate is changing and across the landscape? To sponsor this first workshop, I'm going to turn it back to Louis for some additional remarks and to introduce our guest.
Thank you, Mr. Hohenstein. So just a few housekeeping reminders. Questions for the speaker should be entered in the Q&A box, which is on the lower half of your screen. These questions are only visible to the presenter, the host, and the chat moderator, and we will try and address as many questions as we can. We encourage you to ask anything that will help you understand the topic. We will respond to as many questions as possible today, and unanswered questions will be used to inform future presentations in the series. This is a science webinar, so our speaker will not be addressing US government or USDA policies on climate change. So on to the webinar. For more than 30 years, Mr. Keith Dixon has been a research meteorologist and climate modeler at NOAA's Geophysical Fluid Dynamics Lab located in Princeton, New Jersey. Before joining GFDL, Keith earned his undergraduate and graduate degrees in meteorology from Rutgers University. He taught a bit at Rutgers and briefly worked as a radio broadcaster in the northeastern US on meteorology. His research has focused on using state-of-the-art computer models to gain a better understanding of the factors that influence our planet's weather and climate over timescales of seasons to centuries. In addition to his core research activities and publishing in the peer-reviewed literature, Keith participates in educational and outreach activities ranging from collaborating with museums to delivering briefings on Capitol Hill to presenting webinars such as today. His research and communication efforts aim to enhance the transfer and translation of high-quality, scientifically credible information as it flows from the climate research community to that of local-scale impacts and planning applications. An overarching goal of his is to produce data, information, and knowledge that is useful, usable, and was recognized when Keith was named NOAA's Office of Oceanic and Atmospheric Research as the first winner of the Daniel Albitron Outstanding Science Communicator Award. This is for achievement in communicating NOAA's science and research to non-scientific audiences. So Keith, take it away.
Okay, well, thank you, Louis, for the introduction. And I want to thank the organizers for the opportunity to be the first speaker in this interesting seminar series. As you may have picked up from the introduction, I've been a climate researcher at NOAA for a number of years now. And during that time, I've gotten to work with a really great group of scientists and some remarkable people and learned a lot from them. And that's not just folks at NOAA, but internationally, because the topic we're going to discuss today is one that really is an international enterprise. And with that, we can probably move to the first slide. I'll go on to say that it's people in this field that have tackled the science and advanced the understanding of how this big and complex thing that we call the global climate system, how it operates. And the scientific pursuit has societal relevance, and that's what I'll talk about today. All right. So I'm going to be aiming to convey some information about what is known scientifically, the foundational information, how that knowledge is developed, and along the way, I'll talk about levels of certainty and uncertainty. At times, I'll make reference to a three-legged stool analogy to talk about three areas of focus in the field. So we learn about the climate and climate science system by observations, by computer modeling, and the third leg I show here says theory, which is basically developing a better understanding of the physical laws and what they have to say about how the different parts of the climate system interact with one another. And I'll contend that progress is made in this endeavor to the best extent when all three of these tend to advance together and tell a consistent, compelling, scientifically testable story that adds to our knowledge and understanding. That said, inquiries of this type often start with the big picture first, right? So for climate science, that means we start looking at the planet, at the global climate system, and then work our way down to the more regional and local scale impacts that are more interest to decision makers and society. So here in this schematic, my expertise and my experiences lie in the left-hand box, the one labeled upstream climate science. That's where we do research into how and why the climate has varied in the past and how it may change in the future, with one key set of products coming from the upstream science being numerical projections of 21st century climate change, how the atmosphere, ocean, land surface, and other things change. And it's that output from the upstream climate science that becomes the input into what I've labeled midstream applied science studies. These are the people who address questions that are formed along the lines of how will projected climate change affect fill in the blank, where there's a lot of things that can fill in the blank, things like crop yields, wildfires, the geographic range of different species, or human health, coastal erosion, et cetera, and you get the idea. So the folks occupying the midstream applied science box aren't necessarily climate scientists themselves, but they use climate information. And on the right-hand side, I'll make the case that it's the applied research that can be of most interest to decision makers, the people who are looking to make plans to increase resiliency and to adapt to climate change. And the arrows in the figure are there to represent the linkages between this interdisciplinary enterprise. And I'll make the contention that the stronger the linkages are, the better we're connected on this, the better informed ultimately the decisions and plans can be. Here I have some examples of covers from some reports and documents that represent these three different realms. On the left-hand side, you see a report from the Intergovernmental Panel on Climate Change, IPCC, Working Group 1, the physical science. That's the upstream climate science. And that report is an assessment report, which means it's basically a review of the peer-reviewed literature. It involves hundreds of scientists internationally. It's a big enterprise. It's issues reports about maybe once every 7 years or so, and it's pretty much the gold standard. The most recent report came out in 2021. In the middle, we see volume 2 of the 4th U.S. National Climate Assessment, which came out around Thanksgiving of 2018. And below the words volume 2, you see the words impact, risks, and adaptation in the United States. Now that signals that this document will not just be interested in the global climate, but have a U.S. focus to it. And the word impacts equates to it including information from those midstream studies that talk about the effect of climate change on fill in the blank. And it's organized into a bunch of chapters. Some of the chapters divide the U.S. into different regions and focus on them, but there's also chapters devoted to different sectors. For example, Chapter 6 is titled Forests, Chapter 10, Agriculture and Rural Communities. And over on the right is that Department of Agriculture document referred to earlier by Bill that came out a couple months ago. And from my vantage point, when I look at it, what I see are evidence of efforts to include and make best use of the best available science in order to help inform decisions regarding adaptation and resilience for matters that are of interest to the USDA. Now, going back to that middle box in the previous slide, a National Climate Assessment, that I'll refer to by its initials, the NCA, that and other related reports and other resources lie under the umbrella of the US GCRP, US Global Change Research Program. And that basically involves 13 different federal entities, including NOAA that I work for, and the USDA among them. And that information can be much of it can be found at the website and underneath globalchange.gov. Just a couple examples of things you can find here that you might be interested. I show on the left-hand side of the page, there's a web page from the Climate Resiliency Toolkit. That's a collection of information where you can find things that are aiming to connect the science all the way down to the decision makers and the general public. There's also a report shown here, the Climate Science Special Report. That's also the NCA, but volume 1 that came out in 2017. And that focuses on the upstream climate science, but including the relevance for the US. And on the far right, there's a document that came out in October that outlines plans to improve on the federal efforts to make more climate information more accessible to more people. So all that under the US GCRP banner. So with that, I'll now move on to the climate science topics that I want to focus on in this talk. I've organized things around these three common questions. First question, is our planet's climate changing in unusual ways? We call that a question about detection. It means we look back and see what has happened and see if we can separate the signal from the noise. The second question, are humans responsible for most of the observed trends that have been seen? Well, that's a question about attribution, or you can think of it as a whodunit. Just because something has been witnessed doesn't mean we immediately know why it happened, but there are scientific ways of testing alternative hypotheses. Third question, will the climate trends continue? That has to deal with projections, and for projections, what we do is we turn to climate models, state-of-the-art climate models for which we consider different scenarios and see what they simulate for the climate in the future. Okay, back to the first question. Is our planet's climate changing in unusual ways? And the answer is yes. Emphatically yes. Now, it's true that the climate has always been variable, but the last century or so has been really unusual. There have been changes that have been witnessed and observed that are unprecedented for thousands of years. And these kind of changes that occur just aren't in average quantities, but in the occurrence of extreme events. And they're not limited to the atmosphere, but to the rest of the global climate system. Here's some evidence of that. It's a figure taken from that IPCC report I mentioned earlier. It's showing the global average surface temperature over the last 2,000 years. On the right-hand side, if you look at the bottom axis, you see the time period listed for 1850 to 2020. Now, that's the time since the Industrial Revolution really kicked in. And I'll also note that since the late 1800s, that's the time period where we've had really good thermometer records around the world. So during this period, you can see there's been a steep rise in global surface air temperatures. But before that, like for years 1 to 1850, where you don't have the thermometer records, so that the temperatures have been reconstructed from various proxies. But we can see that while the temperature wasn't totally steady in that past time, there was some cooling after about year 1000. But as you move from left to right, when you get to around the time the Industrial Revolution really kicked in, you see the temperature curve take that quick turn upward, like the blade of a hockey stick, which in fact, figures like this are referred to hockey stick diagrams, a phrase that was actually coined by a former director of my laboratory, Jerry Malman. You can find that on Wikipedia if you're interested. Anyway, the question could be how much warming is going on, and for that, I'll refer you to the vertical axes on that. The figure was originally drafted in degrees Celsius, so on the left, you can see there's been about 1.0 degrees C increase, and then I went in and annotated it on the right into degrees Fahrenheit. And the thing to take away is that 1 degree C warming equates to 1.8 degrees Fahrenheit warming. Now, this plot is showing the same information, but now we're zooming in on the last 140 years. And what you see is that clear upward trend. This is the blade of the hockey stick. But also, now that we're zoomed in, you can see the year-to-year variations and the multi-year variability superimposed on the upward trend. So that points out the value of kind of aggregating information when we're looking to draw conclusions to help see if trend signals exist in noisy data. On this figure, I highlight an 8-year period in the inset, 8 recent years, where if you were only to look at those 8 years, you would say, well, I don't see a trend. But by looking over the longer period, it becomes apparent. The signal emerges from the noise. Another way we aggregate things is, so far I've shown you figures of the global average surface air temperature. So it's being aggregated over the globe. If we were to look at smaller spatial scales, for example, the temperature record for an individual state, you would see a noisier picture, and it might take longer for the signal to emerge from the background noise. So far the figures I've shown have been about global surface air temperatures. That's the thing that people, we get our attention with first. But what makes this conclusion that really unusual things have been happening in the climate system is not just about surface air temperatures. What makes for a much stronger scientific foundation and greater certainty in conclusions is that similar trend signals have been observed in many, many other parts of the global climate system. And it's as we would expect, based upon our knowledge about the way the climate system operates. It's a case where if we refer back to the three-legged stool, where theory and observations are coming together and telling a consistent story. And I have some of these things listed here on the slide. In addition to surface air temperatures warming, the ocean is warming. That's been observed, as is reductions in the amount of snow cover. We're also seeing less ice in the Arctic, and across the globe, glaciers are retreating. Sea level is rising. From basic physics, we know that as the atmosphere warms, it can hold more water vapor, and our instruments tell us, yes, the amount of water vapor in the atmosphere is increasing, and so on. And all the things that we see that are telling this consistent story aren't necessarily a result of scientific instrumentation. For example, from nature, we can see that there have been longer growing seasons. We can see species shifting their range with warming temperatures. They can move poleward or up mountains. And there can also be changing times of some animal migrations that have been linked to it. So A lot of information coming together and telling a consistent and compelling story, a lot of evidence that a good amount of energy is being gained by the planet and the climate's changing. Now, next question could be, well, where's that energy going if the planet's gaining energy? And a lot of people are a little bit surprised by this information. Actually, if we think about the heat that's been gained by the planet, and this figure is showing the heat gain since about 1970 and dividing it up into the different parts of the climate system. And we can see that most of it, 90% or more, has been gained by the oceans. Only about 1% has gone into warming the atmosphere. So that seems a little surprising at first, but basically the way it's going on is that we know that heat flows from warm places to cold places, right? So as the atmosphere warms initially, some of it goes over the ocean, and heat can then flow into the ocean. But not only does it take a good amount of heat energy to raise the temperature of water, which you know from the last time you tried to boil a big pot of water on the stovetop, not only does it take a lot of energy to raise the temperature of water, the ocean also moves in 3 dimensions. What that means is the water that's at the surface today, taking up some heat from the atmosphere, is going to move down and be replaced by water from below that maybe hasn't seen the surface for a long time. There are parcels of water in the ocean that haven't been at the surface for hundreds of years. So the net effect is that the ocean introduces a kind of thermal inertia or thermal lag to the system, or a warming commitment exists in that the atmosphere is cooler than it would otherwise be. For example, if we could do an experiment in computer models and say, what if the ocean had a maximum depth of 150 meters instead of, or 150 feet instead of being its full depth? And we would then see that today's temperatures would be warmer than they actually are because the ocean wouldn't be taking up as much heat. Okay, so this figure, we can zoom down to the US level, or at least for 48 of the US states. And you may be familiar with the term climate normal. Like on a weather forecast, someone might mention that yesterday's high temperature was maybe 7 degrees above normal. Well, those normals are assembled by NOAA's National Center for Environmental Information by calculating averages from 30 years of records. And they update the climate normals once every 10 years. And there's normals that go back to the beginning of the 20th century. On the left, the map here is showing the difference between that latest set of climate normals based upon the years 1991 to 2020. And from that, we can subtract out what was the average temperatures over the 20th century. And you see a red map. Those are warming temperatures. The darkest red representing places that have warmed more than 1 degree Fahrenheit during that period. On the right side, you see the same type of info, but for the change in annual precipitation totals. Now, precipitation in general is a more new variable to look at compared to temperature, especially regarding patterns. I mentioned before that as the atmosphere warms, it's going to hold more water vapor, but that's not going to translate to there being more rain, precipitation everywhere. There's much more meteorology involved in that. But we can see here that a good part of the eastern half of the United States has gotten wetter, larger annual precipitation totals, but not so for the West. And that's because different factors govern precipitation in different locations, and those different things are going to respond to changing atmospheric conditions and climate change in somewhat different ways. And here's an example of how observations can show changes not just in averages, but in extreme events. The quantity being considered is large 2-day precipitation events. You can think of it as storm totals. And from several decades of observations, you can go and determine at each individual location what amount of precipitation falls in the largest kind of storm you see about once every 5 years on average, the 5-year storm. Now, it's going to vary geographically. Some places maybe once every 5 years you see about 2.5 inches of precipitation. Other places maybe 6. But then you can go back after determining that sort of threshold at each location, return to the observational record and determine if those large precipitation events are becoming more or less frequent over time. And that's what's shown here in the map, that those large storms are becoming more frequent in the east, 40, 50, 60, 70% more frequent, but not so in the west. Again, I'll point to different meteorological factors being in play in different regions. For example, it's not unreasonable to think that a lot of those large storm events along the Gulf Coast and the eastern part of the United States can be associated with tropical storms and hurricanes and their remnants. And that's something that's not going to be a factor in places like Utah or Idaho. Okay, that was the first question about the detection problem. Let's move to the second, having established that changes are happening. This is the whodunit question. Are humans responsible for most of the observed changes? And here's the answer. Again, yes. And to use the terminology of the IPCC, it is unequivocal. To use the terminology of the recent National Climate Assessment Report, it is extremely likely, which I think their table says means greater than 95% certainty. And what it is saying is that the observed changes, the things that we've seen, these unusual changes, cannot be explained by natural variations alone. There's a human imprint on them. Determined, well, in order to discuss that, we'll first, and let's think about energy passing through the planet. We need to think about the Earth as an object in space. And it gets, when things are in balance, the amount of energy that's being received by the planet from the sun equals the amount of energy that the Earth returns to space. Your net balance is zero. Things are in balance. But today, as shown on the right, there is an imbalance. And that imbalance is, even with the same amount of sun energy coming in, less outgoing energy is occurring because there's been a buildup of greenhouse gases, which, well, we'll get into that, but they keep things warmer at the surface because less energy is going out. And as I mentioned before, where's that extra heat going that's being retained? About 90% into the ocean. Now, this figure is kind of busy. There's many versions of this out there. This one I took from the NCA report. So I'm not going to go into the details, but just want to mention that we can kind of trace the fate of energy as it flows through the Earth system to see what the budget of the energy of the planet is in terms of the energy. On the left-hand side, it's showing the contributions from the sunlight. And if we figure out what happens to sunlight and sun's energy when it reaches the top of the atmosphere, it turns out about 70% of that ends up being absorbed by the planet. Most of it at the surface, some of it by the atmosphere. The other 30% gets reflected and really doesn't interact with things. Now, of that 70%, that energy that's being absorbed, the planet, to remain in balance, is going to need to return an equal amount to space. And the way that's going to be done, if we go back to our high school physics, the only thing way we can transfer energy through the vacuum of space is through electromagnetic radiation. And given the temperatures on the Earth, that means it's going to be done by infrared radiation, IR, or on the right-hand side of the plot. You may be aware is emitting infrared radiation all the time. You are right now, in the last 2 years, if you've ever had an occurrence to have someone put one of these infrared thermometers against your head to figure out what your temperature is, it's the same thing. It's working on the principle that the warmer things are, the more energy that's being emitted, more infrared energy, and also at a shorter wavelength. So we can apply that to the climate system as well. And the thing is, there's a greenhouse effect. There's a natural greenhouse effect. And what that means is when the surface of the Earth emits long-wave radiation, the infrared radiation, as shown in the plot, only a little bit of that energy escapes straight to space. That's the atmospheric window listed here. Most of it gets absorbed in the atmosphere by various things, by greenhouse gases, by water vapor, by aerosols, and by other things. But the key is those things that absorb that infrared radiation retain it, get warmer, and then re-radiate it, and a lot of it gets recycled and comes back down to the surface, keeping things warmer than they would otherwise be. In fact, I've seen estimates that say, now the average temperature of the surface of the Earth is about 57 degrees Fahrenheit. If we didn't have an atmosphere that had all these greenhouse gases and other constituents that absorb infrared radiation there, the temperature of the surface of the Earth would be more like 0 degrees on average, right? So that's a big difference. What we're going to be talking about today is an enhanced greenhouse effect. What has disrupted this balance? And what we're hypothesizing hypothesizing what the likely suspects are: increased greenhouse gases due to human activity. You have more greenhouse gases in the atmosphere, a larger fraction of the infrared radiation is being absorbed, recycled, leading to higher temperatures. And the prime suspect is carbon dioxide. This plot shows the rise in atmospheric carbon dioxide levels since the late 1950s. It's measured on the top of a Hawaiian mountain, pretty much away from the effects of civilization, so that makes it a good observation site. And you can note here that carbon dioxide, CO2, is measured in parts per million, ppm. And it's now over 400 ppm. Now, though that means it's well under 1% by volume of the atmosphere, CO2 has a sizable greenhouse influence. It doesn't take a lot of it to make a difference. And you can go to the website I show here, an old website associated with those Mauna Loa records, and you can actually get and look at tables and pick off numbers that show the month-by-month trace of what CO2 values are. And here I've done it for different times in my life, and I can tell you that when I was born, that month, the global CO2 level at Mauna Loa was about 314 parts per million. This past July, 417. Seems like a sizable jump. I mean, if a gallon of gas or a carton of milk goes from 314 to 417, people notice. When the carbon dioxide level increases a similar amount, we can assume, well, we can show that the atmosphere will notice. Okay, this is another way of looking at the information from Mauna Loa about CO2. Here we're looking at year-by-year increases. So you can see that the rate of increase has grown over time. In the 1960s, that horizontal bar is right about 0.9 parts per million per year increase. But in the most recent decade, the 20-teens, that's now up to 2.4 parts per million. So not only is CO2 increasing, during our lifetimes, the rate of increase has grown. Now, where does that CO2 come from that's responsible for that? Luckily, there's a lot of scientists who are tracking that down. Large group of international scientists put together the information I'm going to show here. And it's really a formidable task because there's a lot of different sources of carbon and carbon dioxide that go in the atmosphere. It involves atmospheres, oceans, land surfaces, and a lot of things. It's, all three legs of that three-legged stool of observations, modeling, and theory get involved in putting together a budget of what the fate is of carbon that is anthropogenic. And the term anthropogenic means produced by humans. So here on the right-hand side, there's a chart that shows for the decade from 2010 to 2019, where this excess carbon due to human activities is going. So on the left-hand side of that, we can see there's two contributions to adding carbon dioxide to the atmosphere. It sums to about 11 gigatons per year. That's a lot. 9.4 gigatons, plus or minus, are coming from fossil fuels. And then there's the rest of it is coming from changes in land use, which is primarily deforestation, but 11 gigatons total. So what is the fate of that? Well, the blue bar there, representing the atmospheric change, that takes up about 5.1 gigatons of that 11 total. So not half, but getting close to it, 40, 50%. And that is what was responsible for that increase at Mauna Loa, that 2.4% per year increase, 2.4 parts per million per year increase in the atmospheric concentrations at Mauna Loa. What happens to the other part, more than half? Well, that gets taken up by, we say, sinks of carbon in the ocean and in the atmosphere. All right, so I've talked about CO2. It's the prime suspect, but not the only one in this whodunit. There's a number of different factors that we can call radiative forcing agents, things that can alter the flow of energy through the climate system. And in this figure, I realize it's a busy figure, but if you look at the right-hand side, in blue, you can see the carbon dioxide contribution ends up being between about 1.5 and 2 watts per square meter. But it's not the only thing that's changing the flow of energy. There's well-mixed greenhouse gases, an acronym there that's above that. That's also a warming influence, a positive one, but not as much as CO2. But there's also things that people do that have a cooling effect. If you look there, you can see two things below the zero line relating to aerosols. So these are aerosols that are being produced by people largely through burning of fuels. And what happens is, for example, sulfate aerosols. You burn a fuel with sulfur in it, you create sulfate aerosols, and that can cool the planet in two ways. One is a direct way, the aerosols themselves that last in the atmosphere for a few days before they settle out or rain out. They can reflect sunlight. That's a cooling effect. But they also can affect clouds in a way that results in, for a given amount of water vapor, you end up with clouds that have a larger number of smaller drops. And that also reflects more energy and has a cooling effect. But we'd only consider human effects. On this plot, up at the top, the thing that looks like a sawtooth, that's representing solar variability, the 11-year solar cycle. And those spiky things you see down below that are cooling effects are the results of volcanic eruptions. The big ones that spout aerosols up into the stratosphere. So above where commercial planes fly, above where clouds exist that rain out. So those aerosols get up into the stratosphere, hang out for a couple years. And what they do there is they absorb sunlight coming in. So they kind of shade the surface, cool the surface, but the stratosphere actually warms a little bit. So those are the different components, the different things, the different radiative forcing agents that could be suspects in our whodunit. If we put them all together, as has been done here, make it a simpler story, we think of the net effect of the human effects are about, central estimate, about 2.25 watts per square meter. It's kind of like putting a night light at every square meter of the atmosphere that's burning 24 hours a day. But you can also see that the natural effects, the volcanoes and the solar, are small by comparison. Now, the size of that vertical bar for the human effects is fairly sizable. That's an uncertainty range, and most of that is coming from uncertainties about the details of those aerosol effects. Okay, so we have the suspects. How do we test them? Good question. Well, this is where climate models can come in. It's part of the whodunit inquiry. So global climate models in a nutshell, we can call them GCMs. We can do a whole seminar on it, but I don't have time here. We can consider them to be our virtual Earths, our lab, because we don't have a twin planet where we can do experiments on. You can think of them as really big, sophisticated computer programs that run on the world's largest supercomputers. And when I started in the field, there were only a handful of places, including NOAA GFDL, where I work, that were able to do it. But there's now a few dozen places around the world that can do this sort of work. Now, the models simulate the three-dimensional atmosphere, ocean, land surface, and ice. And the atmospheric model component is similar to the models you hear about being used in weather forecasts, but for the climate, more attention and detail is given to the other parts, like the ocean, that have a bigger impact on the long-term climate. And another way to think about it is we take the globe and we divide it up into millions of grid boxes, more than shown in this schematic. And in each of those grid boxes, we consider equations that represent physics. The boxes might be something like, say 50 or 75 miles on a side. Those physics that are being represented, we start with things like F equals ma, the laws of thermodynamics, the equations of motions for fluids on a rotating sphere, et cetera, that are going to represent what the fate is of various things in the atmosphere. They're going to simulate what happens. We don't plug numbers in for temperatures or winds. The models simulate it from some basic forcings. Now, the physics handle most of the things, but given grid boxes of that size, there's things that it can't do. It can't trace each molecule of water as it evaporates from a whitecap over the ocean. So there's things we call parameterizations that would say over that grid box, for a given surface air temperature, water temperature, wind speed, humidity, sunlight, et cetera, this would be the amount of evaporation that would occur. So there's all these equations in here, and basically they're representing how heat, water, energy in its various forms, and mass flow through the system, simulating clouds, precipitation, the creation and melting of sea ice, winds, ocean currents, all that at each of the grid cells over time, marching through time. Okay, bottom line, much more than a spreadsheet in terms of what kind of model. It's physics-based. And how we use that model is related to this whodunit question. I'll summarize a whole lot of GCM experiments here. it is that we can run two types of climate model experiments for this whodunit. In truth, there are more, but this will summarize it. In one case, we can take our model and we can say, we're going to run you and you can simulate a world in which there are only natural variations in those radiative forcing agents. We're going to hold greenhouse gases constant. It's as if people didn't do anything, and we're going to put in the volcanoes and the solar variability that's been witnessed, and we're going to run that forward. And we're going to simulate that, not just at GFDL where I work, but around the world a number of times. And then another way we can run the experiment is we can do the kitchen sink. We can include all those forcing agents, those different things that affect the flow of energy through the system, and run that experiment. Greenhouse gases that warm, the aerosols that cool, the volcanoes, and the solar variabilities in there too, and run those as well. And then we can compare it with observations. Well, on this plot, the observations are shown as the black line. And I think what you can see is that after you get to about the latest 60 years or so, you can see that the natural case, that's the lower one, doesn't match the observations anymore. It stays relatively steady. There hasn't been anything in nature that would cause things to warm, but the model simulations that include all the forcings end up having an upward curve, much like what's observed. So there's a short way of getting to the part of the whodunit. The greenhouse gases are the thing that are given the positive. Okay, on to the last question. Will the climate trends continue? Answer, yes, for two reasons. One, I've kind of alluded to before. Past emissions have occurred, and given the thermal inertia of the ocean that's introduced into the system, the Earth isn't yet in balance. So there's some more warming coming regardless, even if we are able to hold greenhouse gas levels at today's levels, which isn't exactly happening. The other thing is that the pace of emissions in the future will also affect things and determine future warming rates. Regarding the uncertainties, here I'll talk about 4 types of uncertainties you might be interested in, 2 of which really have to do with climate science and 2 of which don't. The first one has to do what will be the future emissions of greenhouse gases. Now that's a question about what people will do, not about the physical climate science. So we can think of that as scenario uncertainty. The next 2 do have to do with the climate system, because even if we pick just one scenario, here's how emissions are going to change, and if we use that to drive, those GCMs in different parts of the world, a different research center, the details of the response to a given scenario are going to differ somewhat. There's going to be warming, but it's going to be within a certain envelope of how much, and the patterns can be a little different. So we'll call that model uncertainty. Third question is, what will the flaps of the butterfly wings do? By that, what I mean is there's natural variability. It's occurred in the past, and it's going to continue to occur, and it's not necessarily predictable. So there's going to be things that come and go, volcanoes and other things that are going to affect the evolution of temperatures on the planet. That's a climate issue. But the fourth one that a lot of you are going to be interested in is, well, okay, I'm not so interested in just temperature and precipitation. I want to know how it's going to affect things I care about. So the question of how will changes in the climate affect crops and other things, well, that goes to the middle box. The midstream applied science applications with have their own uncertainties in translating climate signals into changes in things people care about. Here's a figure I'll touch on briefly, showing how human activities can affect different scenarios. This talks about 2 of the uncertainties in the system. The different colors represent different scenarios, that what will people do, from low to high emission scenarios. And then if you look at the colored bands, the faint colored bands that surround 2 of those, that gives an idea about the spread of those different climate models run at different institutions. So from low to high, you can see there's a large difference depending upon what people will do in terms of emissions in the future. But even given that, there's going to be a certain range where we can't nail it down to a specific number. And it's not limited to just surface air temperatures. This is showing similar values for Arctic sea ice in the summer, which has implications for the environment, commercial shipping, military concerns, etc. If one of your questions might be, is the climate on a trajectory where we might have an ice-free Arctic in the summertime? Well, there's simulations that give us ideas about how that may occur. Here's another plot. This shows annual mean total soil moisture changes at the time when there'd be about 2 degrees C warming around the globe. Different way of looking at things, but it's a factor that doesn't just have to do with precipitation, but also evapotranspiration. The blue-green areas are places that would be getting wetter in the future. Remember before I said the patterns for precipitation could be interesting. For example, it's happening in the center of Africa in the Congo region, but around the Mediterranean, you can see the projections would be for things to get drier there. You can go down to the US level, this taken from the National Climate Assessment Report, just showing the difference between 2 different emission scenarios, the what will people do question. Depending upon that, you can get values for a given case of 8 degrees warming Fahrenheit, or maybe 4. And here's the last map I'll show. You can see it's a more complicated issue when it comes to precipitation. Blue-green showing wetter, but here the dots are showing where there's actually a good amount of information pointing in that direction. So for spring and summer, Alaska from this would be saying, yeah, more precipitation. But the diagonal cross-hatching are areas where the simulated changes don't agree enough and aren't large enough where there's really not much to say scientifically at this current time in terms of what the signal might be. Okay, so from there, I hope you got an idea about this idea about how the upstream climate science is set up, what we know, how we know it, and where the uncertainties lie, and how that information can move then to the applied science research. In that regard, I found a few papers that I thought might be of interest as examples of this process related to USDA concerns. Shown here. What they have in common is that they're focusing on factors in the US, and there are applied studies in which they're looking at the effects of climate change on things where they're using those climate model projections as input to their studies. And one thing I'll just mention here quickly is that they're often not using the raw results from those climate models. If you remember, I said the grid boxes might be 50 or 75 miles on a side. That doesn't give fine enough detail. And so there's often a process goes on called statistical downscaling and bias correction, where additional processing of the climate model results are done in order to bring them more in line, to make them more suitable for use as input into applications like many of those that could be of interest to the agricultural community. So there's an additional processing step that can occur. Okay, and how's that information gets used for decision makers? Just to introduce some terminology I think we've heard before. Some people are interested in mitigation. Mitigation being actions that could be taken to reduce the amount of climate change that would happen in the future. You can also be interested in adaptation. Changes have occurred or continuing to occur. So what can be done? What intervention can be made to reduce the vulnerability of natural and human systems to the effects of climate change? And this is where, if we go to the question of what role can climate science and modeling play in decision support, I'll just relate this anecdote, trying to go from the best available science to actionable science. Several years ago, after some major reports came out from the IPCC, I happened to have a conversation with a well-positioned congressional staffer from one political party who was interested mostly in mitigation of climate. And what he told me was that, the large-scale science is done. You people have done a great job, you scientists. You answered the 3 questions we had. Yes, the climate's changing. Yes, it's mostly due to human activity, and there's more in the future. So now the ball is in the court of the policymakers to do with it what they want. They have the information they need. But he was thinking most about mitigation and policies and treaties. Interesting, within a couple months of that, I talked to another staffer. She was from another political party, but what she said was, because she was mostly interested in adaptation, was, I don't think you scientists realize what you've done. By answering those same 3 questions, climate's changing because of people, there's going to be more. You now are going to see that there's going to be a demand for information that you may not be able to meet. We're not talking about global things. People want to know what's going to go on in their own zip code. So that's where we are. There's both mitigation and adaptation concerns. And that's what I've been trying to give a presentation here, where I think in the seminars that are going to follow, people are going to pick up and talk much more about those other boxes. But I try to give you an idea about where the upstream climate science lies. And with that, I'll thank you for your attention.
with that, that does conclude today's call. Thank you for your participation. You may now disconnect.